And we're back again with another Cafe Yocto episode featuring the phyCORE-AM62x system on module and development kit. Today we're going to be talking about Blink, which I like to call is the HelloWorld of embedded systems. It's our simplest way of exercising control over hardware. So this is a good place to start here in the application development section in the phyCORE-AM62x developer wiki. If you actually joined us in our last video, we did talk about GPIO control a little bit. We did that via the sysfs interface in Linux. This time we're actually going to bypass Linux kernel drivers. We're going to go straight into controlling these GPIO modules within the processor directly with register access. These are physical addresses in memory that give us the ability to control these modules. We're going to be doing that with C code today too. So before we can start running software to blink an LED, we got to hook up an LED. And whenever you're working with embedded systems, my recommendation is pulling up some kind of equivalent of these, let's see, 5 documents. So you're going to need schematics, and because you're working with a phytech development kit, that's going to be in the form of 2, or actually 1 SOM schematic and 1 carry board schematic. These guys are watermark confidential. You'll get them released when you register your development kit that you purchased through phytech. And then since we're controlling the AM62 processor, we're going to need documentation on that guide by itself. And that comes from the silicon vendor, here in this case Texas Instruments. This data sheet here is a great overview of the subsystems within the processor, ordering information, packaging information, and pin multiplexing. And then the technical reference manual kind of has just about everything you could imagine in here. So this is like a 12,000 page document. I often work with the data sheet, which is much shorter, and kind of use them in tandem, dance between the two. This one's just a great quick reference for pin muxing, and then this has like everything you could hope for. And then the final document you need is going to be this component placement diagram. So this is going to really connect up what we see in the schematic. So for example, if I scroll down to our expansion connector, which we'll be using in a little bit, I can search that reference designator here, and I can find certain components on the board, on the top or bottom. So we got both here in the same component placement diagram. And you can see my text is upside down. That's because I rotated the board to be in the orientation that I'm going to be looking at in a little bit. So that's why the text is upside down. Anyway, what I wanted to showcase here is note that the schematic shows X17 with pin 1 in the upper left. Well, let's look at this in the component placement diagram. That is actually in the upper right with the physical hardware. So we actually, this is just to showcase and really drive home the point that you need to rely on the component placement diagram to find your components and then find their individual pins. You can't rely on schematic to help you determine where pin 1 is, because you'll get the wrong signal when you connect up expansion boards or what have you into these headers. Okay, so these are the documents we're going to need. Now let's start talking about where we might hook up an LED. So I got my board over here. Before we hook up LEDs, right, the first thing we want to do is we want to power off the development kit. And so we can do that really easily here. Let's do it together. We're going to walk through the whole process as a team. All right, so now with that off, I'm going to disconnect the power, anything that provides power, so both the USB, UART, and the power supply itself. And remember, pin 1 is up here. Let's just pick a pin. Let's pick a pin. I'm going to pick this one. I flip the camera. So this, I'm looking at X17 here. We're going to grab this guy. How might I go about using that? Well, first things first, we got to double check how the current design, the current implementation is using this, because it is on the carry board. So the good thing here, this signal comes straight from the SOM connectors, we can see here, straight to that expansion header. So we could kind of conclude that that signal is not being used anywhere on the development kit. Now let's follow that into the SOM schematic. So D60, note the SOM pin because the signals don't always stay the same. The name, and it's the same name in this case. So Continuing on, so it appears here at the SOM connector and then straight out of the AM62 processor here at the reference designator U6. So that's a good sign. This signal is essentially brought straight out to that expansion header, and it's not being used anywhere that, as far as I can tell. Now, a good next step would be to check the Linux kernel, make sure that it's not pinmuxed for whatever reason. But in this case, trust me that that's not. I'm hoping to make another video in the future about pinmuxing and the Linux kernel specifically. But in this case, we can trust that this pin is not being used. And what we could do now is let's go look up a little more information about this here. So we can grab the processor pad number here, and then we can search that in the datasheet. And if I select like ignoring things where it's just a substring, I think this would be the first hit right here. Yeah, and so this would be A12. Here's the pad name, which should match what we see here. And looks like this particular signal has, this is reflective of the net name used in the phytext schematic, but it looks like this particular processor pin does have a mux mode that is a GPIO. So this is great. This is an MCU GPIO 0 instance number 23. So this MCU is just the like an MCU domain. There's real-time cores available, and so this GPIO subsystem is in that domain, but it shares an interconnect with all the cores, so we'll be able to control it all the same. So now let's hook up our LED. So we already turned off the system. We can go right into connecting it up. Right. So we have identified our pin. Now we need to count out that pin that we want. So remember, we want pin 9 here at the expansion header. We've determined that this is good and it has a GPIO mode, mux mode. We really want pin 9 and 7 to connect up our LED. But remember, pin 1 is in the upper right, so I just want to recap that. All right, so I got my LED, handy dandy, and here we go. Hopefully I got the polarity right. Double check that later. Now, if I'm starting in the upper right, we got 1, going down 3, 5, 7, 9 for power, and then 7 for ground, so right next to them. All right, LED's all hooked up. Now we could run code on it, but let's look at our code and understand what is happening in there. So let's go through this code line by line together. So at the top, we're just including some headers. These are really going to give us like access to these functions like memory map and the memory management header, file control. We can like open files and time, give us like clocks per second. Really the juicy stuff in this code happens here. We already walked through picking out a pin that we want to control, following it to the processor, identifying if it has a GPIO mux mode. Now what are these next lines here? Well, in order for me to control MCU GPIO 0, let's grab the name of that module and search it in the TRM. Like so, and it doesn't take very long. You don't have to let it search the whole document. It's right here at the top in section 2 or chapter 2, the memory map table here. It's going to outline each subsystem within the processor, and then the bank of registers in the memory map that'll enable you to control it. So MCU GPIO 0 spans from this register to this register. Its size is 256 bytes. And we can see that these numbers are actually where these come from. So the bank of control registers start here and end here, and then we're just subtracting the start from the end to give us the size. So the next line here, this MCU GPIO 0 port, to really understand what's going on here, we have to look a little closer at how the GPIO registers work, essentially. So this is the same scheme of sorts for each GPIO module. There's GPIO 0, GPIO 1, and MCU GPIO 0. This is essentially the same GPIO subsystem in the processor, just copy and pasted 3 times. So you can see that the control registers are laid out in the same way for each, and each module just has a different address for control. The registers within it, right, are organized via these offsets. So these are going to span the size of the control bank, essentially. Now let's look a little closer at one of these. So this is one that we're going to need to use. It's going to take a little bit to understand here from just this. This is a little bare minimum, but it's good for my purposes of explaining For GPIO 0, using that as an example, if we want to control GPIO 0 underscore 0, instance number 0, we would actually be flipping and controlling bit number 0 in each of these registers. And we can see, too, that this is how each register is configured. So, for example, the GPIO data, where's the set data? Set data, here we go. We can see that when we write a 1, for example, to here, it would set the output drive state to a 1. So essentially, by writing a 1 in this bit of this register, we could turn the GPIO high. And then if we go down here to clear data, we can essentially do the same. We write a 1, and it turns off the drive state. Yeah, or it clears the drive state. That's another way of saying the same thing. So if I want to turn off GPIO, or MCU GPIO 0 underscore 23, I would just write a 1 here and it would turn that off. So we could essentially reuse the same mask multiple times in multiple registers, and that's where this comes from. We want to control that 23rd GPIO instance. So that means we need to have a 1 shifted over 23 times, and that this is essentially going to be our mask to do various operations on those registers. Now, we need to access multiple registers, right? We need to set up the GPIO as an output. We need to then be able to toggle it on and toggle it off. I already kind of walked through those. The way those are organized, we can kind of see here, starting from the base address, there's offsets that get you to each of these registers. And so direction is a 10 in hex, set data is a 18, and then the clear is a 1C, and that is all reflected here. That's where these values come from. And essentially we'll be able to just add the offsets to the base address to give us the addresses for just setting data, clear data, and direction. So we're going to set up some pointers, define that delay function I mentioned a bit ago. Now we're getting into the actual main loop of the function. So right off the bat, we have to open devmem. This is how we essentially memory map. We first open devmem, and then with that file descriptor, we can use the mmap function and map physical memory into virtual memory, spanning from the start address to or spanning for size. So that's essentially the two arguments that we set up here that are being used in memory map. So now we have GPIO address as the base address of the module, MCU GPIO 0. Once we memory map, we can close that file descriptor. The memory map will be good. And then we, like I said, we're just adding those offsets to the base. And now we have individual addresses in virtual address space for set, direction, and clear. And then now we're actually starting to flip bits. So this one, this and of the not of the mask, this is essentially going to clear the 23rd bit, or, what does clearing it do? Let's go to the direction. Let's see. So a 0, a cleared bit, sets that GPIO as an output. So if I clear this bit, output. And that's essentially what we're doing here on this line. We're setting it up as an output. And then here we're just doing an OR function. So we're going to set the 23rd bit to a 1. And then we're setting the clear address to a 1. So as we recall, this will turn that GPIO high, this will turn the GPIO low, and we're going to do that with a period of like 2 seconds. So it's very simple. Now that we understand the code, let's boot up our development kit. And we're booting to Linux. Let's run that program. Well, first we'll need to compile it. So I got that copied into here, same program, into a blink.c. We can compile it with this GCC, native GCC compiler like so. And let's run. Now, notice my LED is not blinking. Something's wrong. Oh no. Well, never fear. We actually just missed a step purposefully. I want to kind of rewind. Now, recall that we followed that signal at the X17 expansion header back to the processor. We determined that that pin had an MCU GPIO 0 mux mode, but we never actually checked what mux mode we're in by default. So that's actually the step that we're missing right now. So we're controlling the GPIO subsystem within the AM62 processor. the subsystem itself, but that subsystem isn't having any way of getting out to the pins of the processor, and so there's this step here. We got to control the pad configuration, and so the best way to kind of get more information on this, I'd say, is get the pad name, search that over here in the TRM, and actually already have it bookmarked here in section table 6, 2046, and we can see that my pad is here. Pad config 33, that should match. So just sanity checking, making sure that everything is what I expect. Now notice here, the physical address that was also over here, but we are given the register reset state. So out of reset, that register should have this value. Now what does that value mean? Well, it actually gives us a breakdown here, and if you want a little bit better overview of what that all means, just a little bit above here, we can kind of get a general understanding of what each bit in here does. So just kind of walking through high-level overview. We can turn on drive states here. We can turn on receiver states here. Now, so if you wanted this as an input or as an output, right, we'd have to set these bits accordingly on the pad config. There's some other things like pull up, pull down. We can enable a Schmidt trigger, and more importantly, the mux mode. So out of reset, we already saw that. We are going to have zeros in that least significant portion of this value, and that would be the 0 through 3 bits. Now what does that mean? Well, if it's a 0 there, we can see that that is mux mode 0. Now, is that what we want? It is not. We want mux mode 7. So what is the, let's double check again. Let's have another sanity check. What is this value? What is the value at this register on the development kit right now at runtime? Well, the best way to actually check that, there's a great utility, devmem2, and it's actually going to do something really similar to our Blink program. It's going to open devmem, memory map that into virtual memory, and then give us the value. And we should see that this is matching what we are expecting with the out of reset, right? This is the same value here. And we're in the wrong mux mode. We already determined that too. So how do we change that? Well, I like using devmem2 because it can also allow us to write data back. Let's understand where this value comes from real quick. And for that, I like to use my handy dandy calculator app. So let's compare this to this table, like so. Now, first bit that's set, bit 27, looks like the pull up, pull down is disabled. That should be fine. We're just driving an LED. 16, pull up, pull down is again disabled. Well, hang on. The transmit here, driver is it enabled or disabled? Well, bit 21 is a 0. So driver is enabled. That's good. We need that. We probably want the receiver disabled. So bit 18. Bit 18, that's already done, so that's good. Pull down is disabled. Schmidt trigger 14, that's enabled, but I don't believe that'll cause a problem. I think this only really comes into play if the receiver is set up as enabled. So continuing, let's see the mux mode. We're in 0, 0. We want 7. That's going to be like so. And I think that should match now what we are going to cover here in the guide too. So that's how we came up with this value. Everything we're doing is out of the guide. So essentially we just need to write this value back, and we can do that very easily like this. devmem2, and then just give it the value we want. So it was 0x801 4007, like that. And now if we read it back, it should have changed, right? And actually it confirmed that in the output. It kind of reads it back to you when you write too. So now that I have the mux mode properly set so that MCU GPIO 0_23 is coming out, now when I run my Blink program, we have blinking. Let's go.
Thanks for joining us for episode 4 of Cafe Yocto featuring the phyCORE-AM62x. Stay tuned for the next one where we'll be at the halfway mark of the series. See you then.